Last time we talked about the calculus of rainbows. We're going to continue that today. The main focus last time was why do you see rainbows in a certain spot in the sky, although we didn't quite fully get to the reason for that. We talked about this diagram that you see here, showing that if you've got a ray of light coming from the sun, that's when the sun is low on the horizon, so near sunset or near sunrise, it hits the water droplet here at a certain angle of incidence. This angle that you see right there was labeled alpha. That's the angle of incidence. And because of refraction, which really results from the fact that that light actually travels slower through water than it does through air. I don't know if you ever knew that before, which sounds a little strange because you might also have learned that light travels at a constant speed. That actually is only in a vacuum that it travels at a constant speed that we call c, the speed of light. When it travels through even the air or through water, it slows down a little bit. And it slows down more in water than in air, and so it bends, okay, for some reasons I won't get into. So it refracts, it bends, so it bends once here, and this angle right there is alpha minus beta. And then it reflects, if we're after where's the rainbow is at, we ignore the part of the light that refracts back out of the water droplet and focus on the reflection part of the light before it refracts again and heads to the observer down here. Bends by alpha minus beta first, then it bends by this much, which is pi minus 2 beta, and then finally it bends once more, this much, by alpha minus beta once again, where Snell's law says that sine alpha is k sine beta. Beta is a little smaller than alpha, so sine beta is a little smaller than sine alpha, which means k needs to be bigger than 1. And for water, it's about 1.333, 4/3 approximately. Not exactly. We came up with this formula for the angle of deviation. How much does the light ray turn in this diagram in the clockwise direction from the original direction? D of alpha, it's a function of the angle of incidence. It depends initially on both alpha and beta, like that, but because of Snell's law, we saw that that's essentially like a constraint that helps us write this function of two variables as really just a function of one variable, a single variable calculus function. Because of this constraint, you can solve it for beta and get beta is inverse sine of sine of alpha over k. And when k is bigger than 1, that can't really be simplified. You just have to work with it as it is. We ended up seeing that the critical point, when you plug this in here in place of beta to get a function purely of alpha, and you differentiate that function of alpha, set the derivative equal to 0 to solve for the critical point. Going off of memory here, we ended up seeing that the critical point was alpha is inverse cosine. I think it turned out to be square root of k squared minus 1 over 3. We're going to do a similar derivation for the secondary rainbow today, but first we want to understand where the colors of the rainbow come from and why they are in different angles in the sky. That was the critical point. And when k is approximately 4/3, that gives alpha in degrees as approximately 59.4 degrees. It was a little over 1 radian. And the minimum value of d of alpha, the minimum value of the deviation is the approximately 138 degrees. And what we finished off with is trying to start explaining why this is important. That's what the project talks about here. The significance of this is that when you're near the critical point, the derivative is approximately 0. And so the slope, well, of the curve at the critical point is 0. But when you're close to the critical point, the slope is still close to 0. And the author here phrases this as meaning that many rays, effectively in the diagram, it's like you're imagining infinitely many rays that are more concentrated. They're going to end up exiting the raindrop in a more concentrated fashion because their deviation is going to be approximately the same. Many rays with angles close to 59.4 degrees become deviated by approximately the same amount. Why? We thought about it graphically. The graph of d of alpha looked about like this. Near this critical point, if you plug in many angles, so to speak, a relatively wide interval of angles into this function near this critical point, the outputs are very close to the same value because the graph's so flat near there. You're right, if the graph was exactly horizontal, if it was a constant function, no matter what the input was, the output would be the same. This is not constant, but near the critical point, it's close to constant. And so for a wide range of angles of incidence, you get approximately the same angle of deviation. So the light rays are more concentrated at that angle. Back in this picture, for a relatively wide variance in the angle of incidence, light rays coming in a wide range here, the total turning of these light rays based on refraction and reflection is approximately the same, meaning they end up exiting the raindrop at approximately the same total turning, same angle, which means coming to this picture, which is a new picture, that angle is about 138 degrees. That means that this angle, look, you've got parallel lines and a line crossing two parallel lines. This angle and this angle both have to be 138 degrees. And since this total angle is 180, this one here has to be 180 minus 138, which is 42 degrees. And that would be the angle that you would see the rainbow in the sky at about 42 degrees, almost 45 degrees. And it's not just the top of the rainbow, it's the sides as well. They're all at an angle from your field of vision of about 42 degrees. From the horizon? From the horizon, or from, probably a better way to say it is from whatever angle the sun is at. Oh. And if the sun is effectively on the horizon, yes, it would be essentially from the horizon. The sun's a little higher in the sky, then it would be with respect to the light rays coming at a slight slant, and the angle would be not with respect to the horizon, but a little lower. So good question. But the colors are, and they're in slightly different places. So what accounts for that? On the second page, we get into details about that. And we already kind of addressed this because in Mathematica, our computer program, we allowed K to vary. Well, I mean, right here, we allowed K to vary as well. Right there, here and here. The critical point and the minimum deviation really depend on K. And what this part says is that different colors have slightly different Ks. And that's what Newton discovered when Newton made light rays go through a prism, is that they bend different amounts. Evidently, the frequency of the light affects how much it bends. In his prism experiments, the index of refraction is different for each color, slightly. For red, I should make that red. The refractive index is a little less than 4/3, 1.3318. For violet, I've got purple. For violet, it is bigger than 4/3, 1.3435. Repeat the calculation for problem 1 for those values of K and show that for red, the rainbow angle, meaning the angle off the horizon to the red, is about 42.3 degrees higher. And for violet, it's about 40.6 degrees. And for other colors, it's something in between. So how could we, in a sense, solve this quickly with Mathematica? So here I've entered the function again. It's a function of alpha. K is really a parameter. This is really a family of functions, just like we talked about. Was that on Monday or last week? I forgot. For families of functions. One function for each value of K. Can Mathematica solve for the critical point? Let's see. Take the derivative of this with respect to alpha, set it equals 0, and solve for alpha. And a reminder, when you use solve, you need double equal signs. Okay, gave me a little error. What's the error? It's just saying inverse functions are being used. You might get more than one answer, and we did. Which one of these is the one we want? Looks like this one's the one we want. That is the critical point in terms of alpha. Maybe I'd call it alpha crit. In terms of K, excuse me, as a function of K. I could plug that in, enter it, and then I could evaluate that for different values of K. So like 1.333, it's about 1.0366. I can also figure out what it is in degrees, multiplied by 180 over pi. There we go, about 59.4 degrees when you use K equals 4/3. Now we can quickly solve for these other values of K. For the final answer for the actual rainbow angle, we'd want to, let's see, we'd want to plug that into D and subtract from 180. Okay, that's a little tricky. 180 minus D sub 1.3333 of 59.393, though I do need to convert that to degrees by also multiplying by 180 over pi before I subtract from 180. That didn't work. Oh, that's because this is in degrees and I need to have it in radians. Let's see. What was it in radians? 1.0366. So this should be close to, what was it? I forgot, 42 degrees? Yeah. That's the rainbow angle when you use K equals 4/3. Now let's do the other ones. So we'll start with red light. K is 1.3318. So I guess I should do this, 1.3318 right there. Right here. So it's a slightly bigger angle there, right? Is that slightly bigger? 3318 here, 1.03813 here, 42.3 degrees. Yep, that's what it says the answer is. 42.3 degrees right there for red. You see it? That's for the red one. And now for violet, K is about 1.3435. Do all the same kinds of things again. Plug in 1.3435 here. That represents K. That's the refractive index for violet. The critical value of alpha went down. Smaller angle of incidence that gives a minimum deviation. In degrees, that's, oops, need to change this number. Yep, it's a little smaller. Plug that into D and subtract from 180. There we should get, hopefully, 40.6. Nope, we didn't. What did we do wrong? Oh, I plugged the wrong thing in here. I should have plugged in 1.02628. There we go. Yep, 40.6. If you are trying to take notes on this, This is alpha as a function of K. This is the K value for violet. Here I'm just converting it to degrees. This is in radians. This is in degrees. This represents the angle of incidence, the alpha value, that gives the minimum deviation for violet. Plugging that into the deviation function gives me the actual minimum deviation in the ballpark of 140 degrees. This is what this quantity would be around 140. I subtract it from 180. I get 40 for the angle of the violet. So it's a little smaller. It's a little lower in the sky. Red would be on top. Violet would be on the bottom. I don't remember offhand if that's really the case. It must be. Ultraviolet. Yeah, I mean, technically it goes into non-visible wavelengths as well. You keep going down violet, there would be ultraviolet below that, but you can't see that. Above the red, there would be infrared, but you can't see that.